Okay, thanks very much. So I'm pretty excited to speak about this topic because this is a paper I wrote with Damick Davis, my colleague at Cornell, about a year ago, and this is the first time I actually get to speak about it. I had plans to speak about it in other places, but then the world ended, and then so this is the first time I get to speak about it, and I like it very much. It was recently accepted with minor revisions to Foundations of Computational Math, so I'll give a reference at the end of for the paper. It's available on arXiv as well. Okay, so I only have 8 slides or so. They're a bit dense, but so feel free just to interrupt me and ask questions. So it'd be nice to have a kind of discussion, more so than me just kind of speaking. Okay, so let me tell you what this talk is about. So there's been a realization over the past, I don't know, 5 years or so, kind of starting from the machine learning community, which is the following. It's written on the screen. It says that simple algorithms, so I'm going to explain what that means, for minimizing twice differentiable functions, twice continuous differentiable functions, avoid all strict saddle points when randomly initialized. Okay, so I need to explain what those words mean. Okay, so what does simple algorithms mean? Well, gradient descent, coordinate descent, proximal point sorts of procedures. The classical guarantees say you start, these sorts of algorithms and you converge to a point that's critical. So the gradient is 0. And so the question is, do we really converge to such points, or are there some critical points that you can escape from? Okay, are critical points really attractors of these sorts of procedures? Because some critical points, there are even local maximizers. So can you get stuck in those? Okay, and so there's a special class of critical points or saddle points that are not attractors in a kind of generic sense. Okay, so a strict saddle point means it's just the critical points that has negative curvature. Okay, so roughly speaking, what the realization is that if I give you a C2 smooth function, you're trying to minimize it, let's say with gradient descent. If I initialize it randomly, okay, uniformly at random, or whatever, Gaussian, according to a Gaussian distribution, then it will only converge to points that satisfy necessary second-order conditions for optimality, meaning that if any critical point that has a negative direction of curvature, meaning that the minimal eigenvalue of the Hessian is strictly negative, it will not be an attractor of the gradient algorithm. Okay, so that's a very strong property. That's a very interesting property, and the reason why people in data science in particular have been interested in that is that for a huge number of estimation and machine learning problems, you can actually show that they have lots and lots of critical points, exponentially many in dimension critical points, but all those critical points have negative curvature. Whereas the local minimizers, there are very few local minimizers, and all of those local minimizers tend to be equally good. Okay, and so for these sorts of applications, as a result, these sort of simple algorithms that don't reach these extraneous critical points, they're very important because they only converge to local minimizers.
I have a question.
Okay. Yes?
Does a maximizer not have negative curvature?
Yeah, it does.
So a maximizer is a strict satellite?
Depends how flat it is. Sorry, it depends how flat it is. It might not. I mean, typically it would, but.
But would you consider a maximizer a strict saddle point?
No, you would not.
The definition there is
in general. It depends on the second derivative, right? The second derivative could be 0.
Yeah, but your definition of strict saddle point is critical point that has negative curvature. So if a maximizing point is
curvature means the direction in which the Hessian is strictly makes a negative, product.
Thank you.
So if the Hessian is 0, it's not strictly negative. Okay, great. Okay, and in fact, this sort of realization in continuous time goes back probably to Morse. I mean, decades ago. It's essentially a consequence in continuous time for gradient systems. It's a consequence of the Morse lemma, really. Okay, but it's sort of been revitalized recently as a result of this paper of Lee et al. That's in the footnote. Okay, very good. So what is this talk about? Okay, so then the natural question to ask is, okay, are strict saddles, so critical points with negative curvature, okay, whatever that means, negative curvature in a non-smooth setting, are they problematic for non-smooth optimization? So if I apply an algorithm for non-smooth optimization, would it, and I initialize the random point, would it be attracted to bad critical points or not? That's the question. Okay, so I'd like to answer this sort of question for a few algorithms, and I am very happy that Claudia already talked about UV decompositions because they are going to appear here as well. Okay, so before I get to that, I want to give you the recipe for how do you reason about, almost sure avoidance of strict saddle points for smooth problems. Okay, so the way you do it is very classical dynamical systems. So you reduce the situations to fixed point iterations and then apply a very classical theorem from dynamical systems. So let me just outline what that is. Okay, so you say, okay, I have an algorithm. What is an algorithm? An algorithm is a fixed point iteration. So keep in mind, gradient descent for minimizing a smooth function, that's just identity minus eta grad f. Okay, so that's our favorite example, gradient descent for smooth problems. So this entire slide is about smooth problems. Okay, so very good. So the recipe, how do you want to say that this sort of procedures, encapsulated by T, are going to not be attracted to saddle points. The way you do it is you say the following. Okay, so I have this dynamic system, which is just a fixed point iteration. So, okay, so the first step is you argue that strict saddles. Okay, so strict saddle means that, again, the critical point where the Hessian has a negative eigenvalue, strictly negative, and those are unstable fixed points of the Jacobian of T. So you look at this map T, like for example, for gradient descent. You look at this Jacobian and you argue that that if you have an unstable fixed point, then that Jacobian of the update map has an eigenvalue that's strictly bigger than 1. Okay, so if you look at, for example, the gradient descent update, which is written on top there in red, okay, if I have a point where the minimal eigenvalue of the Hessian of f is negative, then, okay, if you compute the Jacobian of T, that's identity minus eta Hessian f. And so if, minus minus makes a plus. And so as a result, if I have negative eigenvalue for the Hessian at some point, the Jacobian of T, that particular update map, has an eigenvalue that's strictly bigger than 1. Okay, so these strict saddles are, in this sense, unstable. Okay, that's the definition of being unstable. Okay, and then you use the hammer. Okay, then you use a big hammer from dynamical systems, which tells you the following. It's called the center stable manifold theorem, and tells you the following. If I have a iteration map T, if I look at all the points, if I look at all, oh wait, I can use my mouse. Oh great. If I look at all the x, so that the limit of the fixed point iteration converges to an unstable point, the set of those initial conditions has Lebesgue measure 0. So the set of initial conditions that are attracted to an unstable fixed point has Lebesgue measure 0. That's roughly speaking, that's a consequence of the center stable manifold theorem. In fact, the center stable manifold theorem is much stronger than that. What it says is that this set W, if I fix the unstable point, that set W is locally a smooth manifold, and it's sort of it's orthogonal. It has an orthogonal manifold, and they kind of they play nice together. Okay, so there's okay. Anyway, I won't get into that. But the consequence, in fact, this W is a low-dimensional manifold, and so therefore has Lebesgue measure 0. So that's how you reason about these things. Okay, so strict saddles are unstable fixed points, and the center stable manifold theorem says that the set of initial conditions attracted to unstable fixed points has Lebesgue measure 0. So if you start at a random point, you will not reach it. Okay, and then so basic, and that's it. Okay, so since random initialization will not land in W, the algorithm avoids strict saddles as long as you initialize at the random, sufficiently random point. Okay. Okay, very good. Okay, so what's very important here is that the proof for gradient descent requires the function f to be twice differentiable. Why? Because if you want to apply a center stable manifold theorem, you need to compute the Jacobian of T. Jacobian of T is the has to do with the Hessian of f. Okay, so this whole reasoning only works for twice differentiable functions. So that's if you look at gradient descent. Okay, so then the next question is, okay, if is negative curvature enough for non-smooth in a non-smooth setting, even in continuous time? So in other words, suppose I give you a non-smooth function and I initialize a subgradient dynamical system in continuous time. I look at the subgradient flow and I initialize at the random point. will it converge to points that have negative curvature? Okay, whatever negative curvature means. And the situation becomes very intricate. Okay, so here's a fun example. So here's in fact just a C1 function. It's not C2. All right. The C1 function, it has negative curvature at the origin. So the origin is a critical point. I'll write down the formula for the C1 loss in a second, but don't worry about the actual formula. But let's look at it. We have a critical point at the origin. It has negative curvature in the sense that if you go along the y-axis, the function decreases quadratically fast. Okay. Oh, but let's look at the gradient dynamic, or the subgradient, well, in fact, the gradient dynamical system. So these are the integral curves of the gradient flow. And what you notice is that there's a whole valley of initial conditions. Okay. Oh, sorry, the whole valley here and the whole valley here that are attracted to the origin. So even though that you have kind of directionally negative curvature for this function, gradient dynamical systems is attracted to the origin. There's a big measure, a set of initial conditions that are attracted to it. Like if the function was C2 smooth, this would not happen. If your function was C2 smooth and you have directions of negative curvature, the center manifold theorem and all these things tell you that this picture is impossible. If you start almost anywhere, you will not converge to the origin. Okay, in fact, this loss is very simple. It's just the square of the L1 norm minus twice x squared. So that's all that function. So this already tells you that there's something interesting going on in a non-smooth setting, even once you leave the C2 world and go to C1. And in fact, okay, for the experts, this example is not so surprising because in the C2 case, the curvature is a continuous quantity, and in this case, curvature is not a continuous quantity. So that's sort of why everything falls apart. Okay, very good. Okay, but the thing to notice that I want to point out is that this situation is highly unstable. Okay, so even though this seems like a very pathological example, which essentially says that the sorts of things we expect to happen that happen in smooth case cannot transfer to a non-smooth setting, this is very unstable. And the reason it's unstable is if you tilt this function slightly, ever so slightly, the origin will no longer be a critical point. And then if you write down the gradient system, you will escape all bad critical points that have directions of negative curvature. Okay, so that's okay. That's not trivial to see, but okay, if you sort of stare at it for 2 minutes or so and start tilt the function a little bit, you'll see the critical points kind of move around, and you won't have this sort of problem anywhere except the origin. Okay, and in fact, I'll prove that's the case. Okay, so this kind of bad pathological situation is very unstable. It does not happen in general, generically. Okay, very good. So, but in general, essentially negative curvature point-wise, okay, if you just looking in a certain direction, is not sufficient to think about critical points that are not attractors of generic subgradient systems, or in continuous or discrete time. Okay, so what is missing? Something is missing. Okay, you need to fill the gap. Okay, and there's some flexibility here. And one way I'm going to fill the gap, is I'm going to impose an additional structural assumption along with negative curvature. So I will think about good critical points as for non-smooth problems as not just those that have negative curvature, negative the directions of second order decrease, but also those that have some kind of structured non-smoothness. And this is exactly the structure that Claudia spoke about. So I'm very happy that she spoke, that I'm going after her. So that's wonderful. Okay, so let me just kind of summarize. Okay, so in addition to negative curvature, I'm going to assume that my function has some kind of structure. Non-smoothness appears in a structured way. And to give a sense of why it's important, so let's look at a different picture. So we have this kind of pathological picture. Let's look at a non-pathological picture. Okay, so we have a function. It's non-smooth along this ridge, along this axis. All right, it's sharp in the opposite direction. It's very smoothly. So it's exactly this kind of UV decomposition that you saw, and I'll define it in a second. But then let's look at the gradient system. So this is the critical point. So is this critical point an attractor of the subgradient system if I initialize it at a generic starting point? Well, here's the flow, the gradient, the flow generated by the minus the subdifferential. And you see that, in fact, the only initial conditions that are attracted to the origin are along the axis. All the other initial conditions go away. You see, all the flow goes away. The only points that get attracted to the origin, this critical point, are just along this axis, and so they have measure 0. So that's a good picture, which emulates the smooth setting. Okay, so what I'm going to do is I'm just going to introduce a definition exactly for these sorts of critical points, and I'll prove that in fact these are avoided by all sorts of algorithms, and then I'll show that this definition of a good critical point is in some sense generic, natural. Okay, so very good. So the idea is this follows. So this like Claudia said, what this is a UV kind of decomposition. Oops. And so essentially what I'm going to let me just introduce. So I'm going to introduce just a slight variation of the UV because it's easier to write down. So I'll say that that we have an active manifold M around my critical point X. If the function f varies smoothly, in fact C2 smoothly, along M, okay, along this axis, and sharply normal to M, and you can model that in there's many different ways to say it, but one way to say it is that if you look at the norm of the subgradients at points outside of M, they're all big. Okay. So if you look outside of M, all the subgradients are big on the neighborhood of the point. That's just saying that it's kind of sharp. Okay, so this is just a slight variation of the UV decomposition of partial smoothness, kind of localized way. Very good. So I'm going to, so that's this extra ingredient. Okay, so with this extra ingredient, so I'll call this an active manifold, basically. So I'll call this an active manifold. And it's a very important C2, everything is C2, along the manifold. Okay. Okay, so with this notion, I can introduce what I will call a strict saddle for non-smooth problems. Okay, so I will say that the critical point is an active strict saddle if, first of all, f, the objective function, admits an active manifold containing x bar. So just like in this picture, I want to make sure there is some active manifold that captures the non-smoothness. And second of all, I'm going to assume that f decreases quadratically fast along some direction in the tangent space. Okay, so let me describe what this means. Okay, so forget about decreases quadratically for a second. So it's very classical that when you look at second order conditions, you should be thinking only about directions along which the subderivative, the first order derivative, vanishes. So in this setting, when you have an identifiable manifold, an active manifold, the set of directions along which the directional derivative is 0 is just the tangent space of the manifold. Okay, and so it makes sense then to speak about, okay, what happens along those directions. So my assumption is that along some direction, sometimes it's called the critical cone, along the tangent direction to the manifold, the function f should decrease quadratically, and there are many ways to say precisely what it means to decrease quadratically, and they're all equivalent, in fact, in this case. And the simplest way to say it is just to say, okay, there exists some curve gamma that's inside the manifold that's 0 at 0. It's tangent to v, and the second derivative of the origin is negative. Okay, so there's along some curve along the manifold, you have negative decrease, and so this is also related to the second order parabolic derivatives. Any way you do want to define second order kind of constructions when you have an active manifold, they all basically give you the same end result. Okay, so that's one definition. Okay, very good. Okay, so this is a definition. Okay, so I'm assuming that I'm making an assumption here about the nature of a critical point. And for the same reason that one should ask of yourself, okay, if we have a C2 smooth function, why do we think about strict saddles as being natural? Like, why is it natural to think about critical points with second order curvature? Well, if this wasn't like a generic property, it wouldn't be very interesting. So for generics in an appropriate sense, C2 smooth function, in fact, every critical point is either a local minimizer or a strict saddle. And the same thing happens here in the non-smooth setting, as long as your function is semi-algebraic. So if your function is semi-algebraic, that just means that it's defined, it's epigraph, can be defined, roughly speaking, through polynomials. Well, so finite union of sets each cut out by finitely many polynomial inequalities. Okay, so that's now a widely used problem class of functions in optimization. So let's leave it at that. Then, as long as your function is semi-algebraic, so non-pathological, then if I look at the full Lebesgue measure set of perturbations, I take my original my function f that's semi-algebraic, and I perturb it slightly, okay, just a little bit. Then, in fact, every critical point is either a local minimizer or an active strict saddle. Okay, so it's important that you allow perturbations. Like in this example, this function is semi-algebraic, and there is a critical point at the origin, which is not a strict active anything. However, if you make a small perturbation, almost all perturbations will have the property that every critical point is either a local minimizer or a active strict saddle in the way that I just described. Okay, so that's a theorem. It follows from a kind of Sard kind of result for semi-algebraic maps. Okay, very good. So now kind of let me move to this. Okay, so that's I have the definition, and now I want to actually talk about algorithms. Okay, so which algorithms can I think about? Well, I'll think about 3 different algorithms, and I'll make the claim that in fact they avoid all active strict saddles. So okay, so I'll think about 3 different algorithms. So I'll think about algorithms that take the following form. Okay, I'm minimizing a function f. Each of these 3 algorithms, it will just replace f by some model of f at the current iterated xt and minimize the model for some simpler models. Okay, so just let's look at 3 classical procedures. The first one is the proximal point. So suppose my objective function f has the structure just the r of x. Okay, so so the first algorithm is just the classical proximal point update. And that to make sense of this, I need to require that R, in this case, is weakly convex, which means that if you add enough of a quadratic to it, it becomes convex. Okay. Proximal gradient is an algorithm for a special class of functions f that have this kind of decomposed form where it's f plus r. So f will be replaced by its linearization, and r will be r, and then you get like a proximal gradient update. And the prox linear update is when you have H composed with C, where H is convex in Lipschitz and C is smooth. And then the proximal linear update is just going to linearize inside. And then that becomes your new model, and then you minimize the end sets. These are the 3 standard algorithms for non-smooth optimization if you have enough kind of structure. Okay, so here are the main theorems. So the question we ask is, do the 3 methods avoid active strict saddles? We know the active strict saddles are generic up to tilt perturbations of semi-algebraic functions. Every critical point is either a local minimizer or a strict saddle. So are they avoided? Well, okay, so here we prove basically 2 theorems. Around each active strict saddle, this iteration mapping is actually C1 smooth. Okay, this is not very surprising. Well, okay. Not completely unsurprising, actually. Well, anyway, it's slightly surprising. Okay, so around each of this active strict saddle point, this mapping is actually C1 smooth, and it's Jacobian. Remember, we need to argue that around active strict saddle, so this S was T, so I apologize for that. So the S should really be a T, big T. That's I took a slide from somewhere else. Okay, so this S was what I call T on the second slide. Okay, and to make sure that to apply the stable manifold theorem, I need to ensure that the Jacobian of the update map of the algorithm has an eigenvalue of magnitude bigger than 1 at around the point in question, and so we prove that. So in fact, the Jacobian of S has a real eigenvalue that's strictly greater than 1, which is non-trivial because it's not a symmetric matrix. Okay, and as a result, we show using the kind of stable manifold theorem tools, we show that if I randomly initialize these 3 methods and I damp them slightly, so instead of doing the full, these 3 methods directly, I take an average, a small average with xt. So I kind of move in the right direction, but I damp it slightly. Then if I initialize around the active strict saddle or uniformly at random, I will not be attracted to it. Moreover, this result holds globally for the proximal point and proximal gradient method. We don't know if it holds true also for the prox linear method. It's kind of an open problem and Yeah, so the reason we don't know if globally proxy linear method escapes active strict saddles is that we don't know if the proxy linear update is a globally Lipschitz map, whereas for the proximal point, proximal gradient, you can show that they are, it's straightforward to show that they are globally Lipschitz. So if anyone knows the answer, that I would love to know. Okay, so that's my talk. The paper is on archive, and it's been accepted with minor, well, yeah, there's a minor revision we have to do for foundation of computational math. Thank you.
Okay, so thank you very much, Dmitry. So now we're open for questions. So we still have time for 1 or 2 questions.
I'm just wondering, if you were applying kind of a stochastic subgradient method, to solve a problem where you've got some sort of randomness in the gradient estimate, would results of this kind say anything about that?
So that's a great question. We don't know. So for the smooth setting, you can prove that stochastic gradient methods also escape. But for the non-smooth setting, it's tricky. It's very tricky because stochasticity causes all sorts of problems, basically. So yeah, so we don't know, but that's a great question to answer. And it would be great to know that.
Thanks.
Okay, so any more questions? Okay, so if no questions, then let's thank Dmitry.